Hello everybody, and welcome to exercise B. This is actually part B of exercise number 1. We are looking at page 58 in the workbook here. Okay, and they'd like us to calculate an improper integral. Let's work through this together. So we're integrating from 2 to infinity of 1 over x ln of x squared dx. Okay, so again, the way to set up an integral like this is as a limit. So we're going to start by replacing that infinity with a b. And then take the limit as b goes to infinity. Two-step process again. Okay, well, the question now is, how do we do that integral that's sitting in front of us? Okay, well, you might notice that a U-substitution is kind of a natural thing to try here because of that natural log being squared. So let's try letting u be the natural log function. If we do that, our du is going to be 1 over x dx, and then to get the dx by itself, we'll go ahead and multiply both sides by x. Okay, so x du is going to be dx. Okay, and if we fill in the pieces here, let's just see where this leads. Our limits are going from 2 to b, and then we're going to get 1 over x. We just renamed ln of x u, so we've now got a u squared in the bottom. And then dx, looking over at our work to the right, is x times du. Okay, and notice that we get some nice cancellation here. The x's go away, which is a good sign that we probably made a good choice for u here. Okay, so we've got the limit as b goes to infinity of, the integral from 2 to b, and then 1 over u squared, we can rewrite that as u to the negative 2, and that'll make it easier to take the antiderivative. And continuing with the calculation, what would an antiderivative for u to the negative 2 be? Okay, well, using the power rule, we're just going to get u to the negative 1 over negative 1. Getting kind of deja vu here. It seems to me that we might have taken this antiderivative a couple of minutes ago. Okay, and we're going to plug in our limits. And now that we've got an antiderivative, we can go ahead and substitute that u back. So u was ln of x, so we'll go ahead and substitute that back in. And we will get, let's see, ln of x to the negative 1 over negative 1, evaluated between b and 2. And notice that we've got a negative power, okay? It's going to make it easier to find this limit if we take that negative power and move that term into the denominator. Let's do that. Okay, so we could rewrite this whole fraction as negative 1 over ln of x. All we really did was, well, we did two things. We moved the minus sign into the numerator, which we can do, and we took the ln of x to the negative 1 and just moved it into the denominator. Okay, and then, whoops. And then we're going to evaluate between b and 2. Okay, you might be comfortable skipping some of these steps. Okay, I'm writing a lot of steps here, and so if you're comfortable leaving some of them out, that's great. All right, so ready to plug in our limits. So the upper limit is b. If we substitute that in for x, we're going to get negative 1 over ln of b. And then if we substitute 2 in, we're going to get minus a negative. That's going to give us a plus 1 over ln of 2. Okay, and last step then would be to calculate this limit. So the second fraction doesn't have any b's in it, so 1 over ln of 2 is not going to be affected by this limit. It really comes down to what's happening with the first fraction. So as b goes off to infinity, notice the ln of b in the denominator, that's also going to get big. So we're in that situation that we've been in over and over again, where we've got a fraction where the denominator goes off to infinity, and so the fraction's going to go to 0. So ultimately what we get here is 0 plus 1 over ln of 2, and that means that the value of our integral is 1 over ln of 2. Okay, and last question. If you look at the instructions at the top of the page, they said determine whether the integral converges or diverges, we got a number, 1 over ln of 2. That's something that you could put in your calculator and get a decimal approximation for. So that means that this integral converges to that number. Okay, and we are done.